Attempting a seamless resize of a distributed cache cluster can, without warning, trigger a collapse of the underlying primary database. When engineering a distributed system, the starting point for balancing load usually relies on basic modulo arithmetic. The logic is straightforward. You take an incoming request key, run it through a hash function to get a massive number, divide that by the total number of servers, let's say 4, and then route the data based on the remainder. Because of how hash functions distribute outputs, this mathematical dependency results in an even distribution of data across all available nodes. In an environment where the server count never changes, this logic works without issue, but production reality involves auto-scaling policies triggering throughout the day and hardware degrading unpredictably. The cluster size rarely stays constant. Treating server infrastructure as a static integer creates a system-wide vulnerability, leaving a trap waiting for the next hardware failure. Consider a standard failure. A single cache node experiences a kernel panic and drops out of the server pool. The immediate consequence is that the total server count, the divisor in the routing equation, decrements from 4 to 3. By changing that divisor, the system recalculates a different modulo remainder for nearly every existing key in the cluster. The surviving cache nodes still hold the data, but the routing layer is now calculating new trajectories and sending client requests to the wrong servers. This specific failure state is known as a cache miss storm. Every misrouted request registers as a miss, bypassing the memory layer entirely and hitting the origin database. Naive modulo hashing fails at scale because a single hardware issue mathematically invalidates the global topology of the cluster. To solve this, distributed systems utilize an architecture called consistent hashing. The objective is topological decoupling, completely removing the total server count from the routing equation. This approach uses a linear hash space, like the output range of SHA-1, and loops it back on itself to create a continuous circular structure called a hash ring. First, the system processes the physical server's IP addresses through a hash function, assigning them fixed positions directly onto that ring. Next, incoming data keys are passed through that same hash function, projecting the data into the same spatial environment as the servers. This establishes a routing rule. Land on the ring at the key's hash position and walk clockwise along the perimeter until striking the first available server. By projecting infrastructure and data onto an independent mathematical plane, data ownership is defined by spatial proximity rather than cluster size. We can test this against the scenarios that broke the modulum approach. First, the scale-out scenario, where a new node is added to handle a traffic spike. As shown in this figure, when server 4 drops into a specific physical gap on the ring, it only intercepts the keys located immediately counterclockwise to its position. Unlike the modulo method, the rest of the keys on the ring maintain their assignments. Now consider the scale-in scenario, where a hardware failure drops a server from the ring. Recovery is automatic. Orphaned keys roll forward clockwise until they encounter the next available server. The failure is physically isolated. The majority of the cluster has no awareness of the outage and continues serving cache hits as usual. Consistent hashing bounds the blast radius of infrastructure churn, limiting data movement to a fraction of keys defined by the ratio of 1 to the total number of nodes. However, these mathematical circles do not guarantee perfectly balanced loads. A standard hash function outputs uniformly distributed values, but it cannot ensure perfectly equidistant server spacing when only a few nodes are placed on the ring. This geometric variance creates an imbalance in partition sizes. As seen here, one server may command a large empty stretch of the hash space, while its neighbors are clustered tightly together. This leads to the celebrity hotspot problem. Highly accessed keys land on one specific server, while other nodes in the cluster remain idle. Physical nodes can buckle under heavy traffic, while neighboring servers have the capacity to help but lack the assigned keys to do so. Basic consistent hashing solves topological volatility, but it does not inherently provide equitable load balancing. To address this, systems like Cassandra and Dynamo use an optimization called virtual nodes, or vNodes. Instead of placing a physical server on the ring once, the hardware is virtualized. The system maps a single server to the ring multiple times using slightly altered identifiers. This technique slices the hash space into micropartitions. By scattering these virtual nodes, the system statistically smooths out the data distribution across the entire ring. Virtual nodes also allow architects to balance heterogeneous hardware by assigning more virtual points to servers with higher physical capacity. This approach increases the metadata management overhead required in the routing layer. Consistent hashing provides a robust, reliable framework for controlled key ownership, requiring these specific optimizations to achieve true production-grade balance. Managing these state management baselines is a core requirement for building resilient, large-scale distributed systems.